Hello and welcome to another Tycho video. In this presentation, I'm going to be talking a little bit about the new features and enhancements that you can expect to see with the newly released 10.6 version. So with that, let's go ahead and get started. So the first item of interest here is the addition of a revised exposure time calculator. So if we go to Calculators, Optimal Exposure Time, the previous version, while it did work, it was somewhat overly complicated. It displayed a lot of unnecessary or not particularly useful information, and it was somewhat, again, just challenging to use effectively. So here we have a new exposure time calculator, and it has a total of 4 inputs. The first of which is the plate scale of the optical system. And if you're not sure what that is for your particular instrument, your particular configuration, you can go to this plate scale calculator. And that basically will prompt for the focal length of the telescope, the micron size of the pixels of the CCD or CMOS camera, as well as any binning that you might be doing. So 2x2, 3x3, and so forth. And then it will finally produce the plate scale of that particular system. So that is the first input. Next, you would then specify the speed of the object that you wish to image. The next 2 inputs concern the streak of the object as well as the minimum movement. So what does it mean by streak? Well, streak would be how much elongation or trailing of the object would be present on the image. So if you take a very long exposure of a moving object, it will produce some sort of streak or trailing effect. A default value of 4 would be ideal. And then finally, the minimum movement. So this is how many pixels does the object need to move in order for it to be detected by the tracker. So typically, I would recommend at least 5 pixels of movement. Again, and this pertains to the overall image sequence. So that this is the total exposure time, not just the exposure time of an individual image. So that will be taken into account. So again, these 4 inputs, and then you simply click refresh output, and then it will compute and display the results. So the first item here is the maximum single exposure time. And again, that relates to basically how long you could expose a single image without exceeding that maximum streak limit. And then the next item here is the minimum total exposure, and that relates to the minimum movement that I talked about just recently. So how long does the total exposure time have to be in order for that object to basically have 5 pixels worth of travel during the sequence. So finally, we then have what it would recommend as an image sequence. So as an example here, you could take 60 2-minute exposures, and it says that if you do that, the object will have traveled 36.4 pixels in the course of 2 hours, which is the total time there that it would take to capture that. So again, that's just a recommendation. There are a number of different ways that you could capture that sequence. And as an experiment, if we wanted to, if we had a faster moving object, 10 arc seconds per minute, what do you think is going to happen to the maximum single exposure time? Well, if you want to still have a maximum streak of 4 pixels, that's going to reduce the single exposure time. So let's see what that looks like here. And indeed, that did update, as you would expect. So we now have 40 seconds as the upper limit on a single exposure time. And here, also that total exposure time has gone down. In order for it to move 5 pixels, it's only going to take 49.5 seconds for minimum total exposure time. And here again, it's going to say what a recommended exposure sequence might look like. So you could, for example, take 100 40-second exposures. And if you did so, then the object will have traveled 400 pixels in 1.1 hours. So that is the first update. The next one I have here concerns the cluster computing module. So let's go ahead and take a look at that. Okay, so this next part pertains to the cluster computing module. Now, if you do not know what that is, just briefly put, this is a way for those who use the synthetic tracking module to speed up that operation. So if you've messed around with the synthetic tracker, you know that it is very processing intensive. And so one of the ways to improve on that is to divide the workload amongst multiple computers. Now, it's been requested in the past to have a way in which to alter how that workload is distributed. As you might imagine, if you have multiple nodes in the cluster and they're all the same performance, it's perfectly fine to distribute that uniformly in an even fashion. But if one node, for example, is twice as fast as another, you would want to allocate that workload such that the faster one has, say, 2/3 of the work and the slower one has 1/3 of the work. So to demonstrate this enhancement, I'm going to go ahead and walk through just a quick breakdown of how this works. So first I'm going to go to the Network tab and manage worker nodes for the cluster. I'm just going to add 2 worker nodes. So the first one will be this local machine here, and I'm not going to be very creative with the naming scheme. I'm just going to call it node 1 and give it the IP address of itself. And I'm going to start off by demonstrating what it would look like with just an even distribution of the workload. So I will give both worker nodes the same allocation of work. So that's the first one, and then we have node 2, and this one is actually running a GTX 970 graphics card. So that means it is actually slower than this first node here, which is running an RTX 2080. So we should definitely see a noticeable difference in processing time between the two systems. Now what I'm going to do before I proceed with this, I'll go ahead and attach a worker node to this machine. So again, I'm using this port number here, and the user guide has more details on this. I know I'm going a bit quickly through this, but I'm just specifying the parameters for this, and I go ahead and add to list this node index here. So I go ahead and once I've done that, I can launch the worker node. And so what that has done is in the background, it's running another instance of Tycho, and I can go ahead and say, yes, it can have access here. So it's listening in the background for incoming connections. So what that means is now I can click here to ping these 2 nodes, and as you see, they are both online. So again, if we wanted to, we could see what kind of spec they have. So that first one is again an RTX 2080, and the second one again is a GTX 970. So that last one there gets a score of around 26,000 on benchmarks, and then that one on the top gets around 112,000, if I'm not mistaken. So again, we should see a noticeable difference in performance between the two. So at this point, we are ready to go ahead and go run through a test. So if I want to, I can add some images to this example here. So I'm just using the DS3 dataset. That's one that you could actually download from the Tycho website if you wanted to try it out. And so if we run it through the synthetic tracker, then I'm just doing a blind search. 121,000 motion vectors will be examined, and I click OK. And it's going to prompt me for how do I want this cluster to operate. Well, I don't really care to add the local machine because that is actually already node 1. And so I'm just going to go ahead and leave that as an unallocated node, meaning just the 2 that I specified and set up, those will be the ones that will be operating. So again, user guide has a bit more detail on that if you need more info, but this is just a quick walkthrough. So now that I've clicked OK, we are ready to allocate the work and start processing. So I click the Start button here, and it has to upload first. Again, that was quick to do so for the first one because that's on the local machine here, and the second one takes a little bit more time because it is in fact a true remote system. So go ahead and give it a moment here to finish up, and here we are. So now that they are both processing, and I'm not going to show the whole however many minutes it would take. I'm just going to show the first segment here of you can see the percentage difference. So that first node here is already at 10%, the second is at 3%. So that gives you an idea the disparity in performance between the two systems. So now that we've shown that, we know what that looks like. Now let's go ahead and experiment with a different workload coefficient. So we'll go ahead and skip to that. Okay, so at this point I have modified the worker nodes such that the first one has 75% of the work allocation and the second one has 25%. So let's go ahead and see what that looks like. So run the synthetic tracker once more, and I'm going to go ahead and proceed with that same configuration. Again, just modifying those coefficients for the workload distribution. And I have to go ahead and start the worker node for the system, and now it is ready to go. So the idea here is we should see similar percentages between the two systems, and as you can see, that does appear to be the case. So even though node 1 has a much faster GPU, it now shares a similar progress percentage-wise with this workload distribution. So now that you've seen that, I'll just basically conclude this with just kind of a quick chart showing the breakdown, what this looks like, and just sort of a benchmarking analysis here. And then we'll go on to the last segment. Okay, so on this slide, this is a benchmark comparison showing the different scenarios that you might envision, with the top one being the GTX 970 GPU. These numbers are in seconds. So it took 816 seconds to process the data set, again using just the 970. Next we have the RTX 2080 GPU, which is much faster, and it took only 243 seconds. After that we have a combination of the two using an even distribution of the workload, and that took 410 seconds. So logically you would more than likely opt to just use a 2080 under that scenario. But with this enhancement, we are now able to distribute that workload such that you can feed more data to 2080 and less to the 970, but still utilize both. And that allows us, in this case, to achieve a result of 208 seconds. So in this scenario, I supplied 75% of the work to the 2080 and 25% to the 970. And that is a nice improvement over just using the 2080 by itself. Okay, so for this last segment, I'm going to be talking a little bit about the auto truncation feature. And now, what does that mean? What does it mean to truncate? Well, in this context, what it means is that we have an object, an asteroid or comet or some other solar system object that has a number of observations or measurements. And so there's some desire to truncate or remove some of those measurements. Now you might ask, well, why would you ever want to do that? I mean, generally speaking, isn't it better to have more observations, more measurements? And that is generally the case, yes. However, there are some objects for which they have a huge impractical number of measurements or observations, and therefore it takes a lot of time to compute their orbit using all of those measurements. So I think it's best to demonstrate this with an example. So I'm going to start off with a main belt asteroid, nothing fancy about it. I'm going to download its observations. This is numbered Minor Planet 38826. So I click OK, and it's going to retrieve all of the observations, all the measurements of this object. They go back to 1996, and I have unchecked this feature here. So this is what I'm describing or demonstrating here, is this auto truncate. Now this used to be simply truncate past 2 years is what it used to be. Now it's a little bit more intelligent about the way it does things. So I'll demonstrate that here. So first, we're not going to do any truncation. So I'm going to just go ahead and click View and Find Orb. So what this means is it's going to go ahead and compute the orbit of this object, again using all of these measurements. Now that didn't really take a whole lot of time, and we used 1700 observations to do this. And you can see here, these are all the measurements and the computed residuals of these measurements. And if we wanted to, we could select multiple at a time and see what those residuals look like. But anyway, the point of this is a fairly mundane, ordinary object, and this is all well and good. You wouldn't really have to do truncation for this example. But if we wanted to, what would that look like? Well, I can click this option, View and Find Orb, and we should get back a result, and hopefully the orbit should be quite similar. You can see we went from 1700 now to 600 observations, and the orbit, does it look similar? Does it look similar with respect to, first off, the errors? Well, we see here that the errors are computed pretty similar, and that gives some confidence. Of course, what we would really care about then are the orbital elements. So we could look at, for example, here the eccentricity, 0.154. Here we have same 0.154. And you could go through this on your own, but suffice to say, yes, they will have essentially the same orbit. In fact, one way to really test that is if you wanted to, you could load up an image sequence and say View Images. And if I wanted to, I could attach the orbit of that first object, or it's the same object, but of the first set of measurements to the data set. And when I do that, it's going to allow me to click on an image, and it will then center the object using the computed ephemeris. Again, that was derived from the orbit of that object. So if it is a well-computed, well-defined orbit, then the object should be well-centered within the crosshairs. And we see that that is the case. And this is again using the orbit computed from the 1700 measurements or observations. Now if we do the same thing for the one that has been auto-truncated to 600, what does that look like? Do we still have the object centered in the crosshairs? So I'm going to do Attach to Dataset. And here we go. Yes, we see that the object is still centered in the crosshairs. Another way to look at that would be the ephemeris X and Y. So I'll just go down to the very last image here. You can see that it has 0.72 and 0.45 for that last image. And if I do this for the other orbit, do we still get 0.72? We have a 0.71. So you can see, indeed, there was a change, but the change was only 0.01 pixel. In other words, for all intents and purposes, both orbits are usable for our purposes here. So the one with 1700 or the one with 600. Now again, it doesn't really matter. You don't really have to truncate in this example because it really didn't take a lot of time to do the first orbit computation. In fact, it went from 43 to, we had a solution. It just took like 1 second to compute that orbit for this object. But what I'm getting at is there are some objects for which this is not the case. So if we go to Tools, Download Observations, there happens to be one here, 85275. This is a 1 kilometer NEO, and so it's an interesting object. It has measurements going back to 1994. And if I do not check this box, Auto Truncate, what happens? So if I go click View and Find Orb, it's going to submit for solving. And we're going to see here that it actually takes a very, very long time to compute the orbit of this object. So I'll go ahead and give it a moment here to try to complete this computation. But again, you can see here already that it's continuing to solve, solving still in progress. So again, I'll go ahead and give it a moment to try to complete. But here we go. It basically expired. So when you use the online solver, there's a time limit. It gives it 20 seconds. If you exceed that, then it just says, well, I'm not going to be able to find an orbit for it in a meaningful amount of time. Now, if you wanted to, you could use the local installation of FindOrb. And so if I wanted to, I could try that. And in fact, I have done that. And when I give it all the measurements, in fact, it actually does not, it will complete, but the orbit it comes up with is not valid. So long story short, let's just go ahead and take a look and see what would happen if I were to then apply Auto Truncate. So I go ahead and check that option here, click View and Find Orb. So main expectation here is that we should, and indeed it is, much faster. So it used 786 of a total of 800 observations. And this is with the truncation. So again, that only took a couple of seconds. Again, the point of this is to demonstrate that we now have a meaningful way we can do truncation. And it's not just truncating back to the past 2 years. In fact, what it is doing is it's going to truncate to the past 10 years. And it's also going to weed out observations that are just, you have some stations that will flood the Minor Planet Center with dozens or hundreds of measurements in a given night, for example. And so you've got a lot of just unnecessary measurements of the same object within a very short period of time from a single station. And so anyway, this is a way to really cull back some of those potentially unneeded observations. Again, so what does this look like? If I download it once more, we can see actually the culprit behind this. So as you scroll through this list, there are actually over 4,000 observations on this object. If you'll notice here, the station number here, C57, that is actually, in fact, if I wanted to, I could probably show it here. Here it is. That is TESS. So that particular satellite is providing a huge number of observations on this object. So that about wraps it up for this video. I want to thank you for watching and stay tuned. There's going to be a lot of exciting updates here in the future, and I'm be really happy to show those as they are made available. So again, thanks for watching, and see you next time.